ఏ యాప్ చేసుకున్నా ఓపెన్ చేసుకున్నా ఇది రీసెంట్ లో పెట్టేసి ఓపెన్ చేసాం ఒక సౌండ్ వినిపిస్తుంది.
మన మాటలు కనపడుకున్నప్పుడు
Hello everyone, very good evening. Let us get started. All right. So yesterday we started a discussion on the multiple linear regression equation, and let us recap what we discussed yesterday. Okay. Yeah, friends, could you please turn off your videos? Yeah, please just check whether your video is turned on or turned off. Please turn off your videos. Yeah. All right. So yesterday we started a discussion multiple linear regression equation. The generic form of multiple linear regression equation is y equal to beta naught plus beta 1 x1 plus beta 2 x2 so and so plus beta k xk, right, plus epsilon naught, that is error. So when do we use this multiple linear regression equation? So in the data set, in the problem statement, if you have more than one independent variable, then we'll go for the multiple linear regression equation. And yesterday we have seen a few examples, and we were discussing about the miles per gallon MPG, okay, of a car based on the other parameters such as the HP, horsepower, and volume of the car, weight of the car, and then the top speed of the car, SP. These are the four variables that we have considered. And then we build the regression equation, and the steps are like this. So we have the data set, and then we have done EDA. We have seen the correlation as well as the scatter plot between all the variables, and we found out that the MPG is negatively associated with all of these variables. Then after that, so we went ahead and built the model, and we found a few problems with the model because the volume and the weight so became insignificant in the output of the regression equation. Then that problem is called as multicollinearity. So that is as part of model validation we found out model validation, right? So then we found out the problem of multicollinearity, so using VIF, variance inflation factor, and also as part of this model validation we did residual analysis or error analysis. So we have done a series of plots. One is error versus, so error versus the fitted value, that is nothing but yi hat, and then the QQ plot is for to check whether the errors are following normal distribution or not. Then error versus xi. So xi means error versus all the independent variables to check. So do we have any patterns in the data, or the model that we have built is a good model and the variables are also good. So that is what we have done yesterday. And today we are going to discuss about model deletion diagnostics. So deletion diagnostics. So as part of this, we are going to identify the outliers and influencers in the data. Okay, so once we find out the outliers and influencers, what we do, we'll go back to the data set, remove those outliers and influencers, and again go through this entire process. Then, so we have to follow this procedure. So as long as we don't find any outliers in the data set, then finally we will build the final model. So that is what actually we are going to see now. So this is a phase we are going to discuss now. Then we'll see the final model. Then use that model to predict or find out for a given car what would be the MPG value for the best model that we are going to find out. Right. So the model deletion diagnostics. So let me have a new slide here. For example, I have a data set like this. So this is X and this is Y. Okay. Data set is like this. So data points. And another data set is like this. So without just these two data points, so this is my data set. Right. So in the absence of these data points, my data sets are like this. Now, when I have the data set like this, my regression equation would be like this. In the absence of these data points, my regression equation would be like this. Okay, so this regression equation 1 and this regression equation 2. So what do you think is the best regression equation, 1 or 2? Could you please post your answer in the chat window? What do you think, guys? So is 1 or 2 is good? Yeah, others. So we have total 109 and YouTube. So only I could see a few responses. We have two options, 1 or 2. So you can just post 1 or 2. That's all right. Okay. The majority people, okay, says 2. Right. Good. Now let us analyze which one is the best one. So if you see here, this regression line. So is this regression line is going through the majority of the data points? No, right? See, we have two data points. So here, to satisfy these two data points, the regression line slope has been increased and it ignored the data points here. Because remember OLS objective is find out a line that gives us the minimum error, minimum distance. So in that process, this regression line slope has been increased and this line has been pulled towards to these data points, two data points. And it ignored the data points that are there here. Wherein, so these data points have been removed from the data set. And when I have these data points, my regression line is settled well in these data points. Now this data point is representative of this data point that we have here. Now, can you say this regression line is a representative of all the data points here? No, we cannot, because so it is very far from these data points. And here I can say, yes, this is exactly middle of, it is going to the middle of all the data points. Now we can say this is the best representative of all the data points that are there in the data set. Right? Now in this case, which one is the best regression line? The best regression line is here is 2. Because if I use this, so I would get more error. So when I consider the data points, so in this area, basically in this region, if you analyze why this regression line is behaving like this, so why the slope is more in this case, the slope is low in this case, because of the presence of there are two data points. So these data points are considered as outliers or influencers. Under the influence of these two data points, the regression line slope has been increased. In other words, you can think of these two data points so have pulled the regression line towards themselves and leaving these data points so behind. And when you say that regression line should be the representative of all the data points in the data set. Okay, like this. So it should be representative of all the data points. But here, because of the influence of these two data points, the regression line has been moved towards them. And now this is not a best representative of all the data points. So we can understand this. So the as a democratic nation here, you can think of this as a leader, regression line as a leader. So the leader should be representative of all the data points, all the people in the society, right? So not a few people, not a few influencers in the society. Now in this case, what is happening? These two guys are influencers. So these two guys are influencing your regression line, your leader, to incline towards them, to bend towards them. So that is not a desired situation, right? Now here what happened? So those influences have been removed, okay? So from the data set. Now in the absence of these influencers, the regression line is well settled in the data points. Now this is the best representative of these data points, right? Now, so what we have to do as part of deletion diagnostics is identify such influential data points or outliers in the data set. So once you identify them, so remove those data points. When I say remove, yes, so you should have a good discussion with the customers and the business teams why these two data points became influencers or outliers. And then, so after that, we can remove those data points. Then, so we can say that our regression equation is well settled and representative of all the data points. Now, how are we going to identify? So we are going to identify these influential data points using Cook's distance. Cook's distance. The other one is leverage point. Leverage points. Okay. Both gives us the idea of whether the data points are far from the mainstream of the data points or they are outliers or influential observations. So both of these gives us that idea. Now, how are we going to find out? Let's say, for example, I have a regression equation. Okay, 100 data points I have in the data set. With these 100 data points, I've built a regression equation. Let us say beta naught value is okay, 51.2 beta naught, and beta 1 value, let's say 60.9, beta 2, so 25.1. So this is what the regression line coefficients with the 100 data points. Then, so I have second regression equation. What I have done is I've taken out one data point. So one data point I've taken out, and remaining 99 data points I've built the regression equation. And with this, so my beta naught value, let us say 51.01, beta 1 is okay, 60.2, beta 2 is so 26. Okay. Then, so again, what I've done is, so here 100 data points, 99 data points. So whatever the data point that I've removed, again, I've included in the data points, and different data point I've removed. That means, so I have a different 99 data points here. So what I've done is, whatever the data point that I've removed from here, that I've included, and a different data point I've removed, and again I have 99 data points. And with this, when I build the regression equation, so my the coefficients are like this. So the beta naught value is okay, 21. Beta 1, let us say that is okay, so a 10.2. Beta 2 is so 1.05. So these are the values, the coefficients, so for the third regression equation. Now a question for you guys. Okay, so which regression equation, yeah, so which regression equation you see is odd? Okay, is it different completely? Out of these three regression equations, so regression equation 1 and 2 and 3, so which one do you think is it different? Right, regression equation 3, exactly. Okay. Because if you see the values, the coefficients, these are in similar lines, and this is a the regression line 3, the coefficients are very low, the slope and all those things, right? Now, so when you say a data point has been removed and I have got these coefficients. So that data point could be this, for example. But when you see here, the coefficient values have been reduced drastically here. So that means the slope has been reduced drastically. So in this case, the data point that we might have removed this or this. So because of absence of this data point, the regression equation would go down. That means the slope is reducing. The slope reducing means the values are going down. So that means, so we are getting this kind of equation. That means when you are getting the coefficients are low, so we can think of, we have removed these kind of data points. So when you remove a data point which is influential or the outlier data point, the regression line would go down. The coefficients R would go up. So based on the scenario of the data points. And wherever you see there is a drastic change in the coefficients, that means you have removed an influential data point or outlier from the data set. And we will measure so how drastic the change is, how drastic or how big is the difference between the regression equation coefficients and the previous regression equation coefficients. Based on that, we are going to identify whether the data point is an outlier or not. So that is what the Cook's distance does. What it does, it removes a data point, build a regression equation and measure the differences, and do that for all the data points. And wherever you see the huge difference between the earlier coefficients and these coefficients, then that means, so we have removed an outlier or the influential observation, and so that would be tracked separately. And similar manner, leverage also, the influential data point we would find out. Right, so this is the Cook's distance. On x-axis, we have all the data points, a row index, all the data points. On y-axis, this is the Cook's distance. If the Cook's distance is more than one, so that you can say that data point is outlier. That means, so this is the data point that we removed when we build the regression equation. So this is one data point. So initially this was like this. And when you remove this data point, there's a huge change in the coefficients of the normal, the regression equation. And after removing this regression equation. So that is what the huge distance here. That is what the outlier here you can say. And this data point is outlier. That means, so here you can see 76. Right, so 76 the data point is the outlier in the data set. That is where you can see the large distance here. So like that, we'll find out the outliers in the data set using Cook's distance. Then leverage. Okay. Leverage gives us the idea of how far the data points in comparison to the mainstream data points. So here the majority of data points are in this range. Okay, so here. And if you see this data point is very far from the mainstream data points, then we can say this is the influential observation or outlier, and this one and this one. So how do we find out? How do we compute that? So we have formula 3 into k plus 1 by n. So this is the threshold value. We will have a cutoff. So k is basically, n is a number of, yeah. So data point and k will compute from this. And then we'll, when you have this, if this value is more than 0.2, okay, 0.2, so then we'll say that those data points are high leverage data points or have high influential data points. So in this case, you can say this and this. These two observations are highly influential data points, and so we can go ahead and remove. Yeah. Right. So as you see here, 76th observation and 17th observation, and here also you can see 76th observation. Right. So this is outlier, and here also this is a high leverage data point, and this is a high leverage data point. Remove 70th and 76th observation from the data set. Okay. So when you remove that, okay, so when you remove that, again we have to go for the model building and we have to check the accuracy. So this process goes on until we don't find any outliers, and then we'll finalize the model. Now let us go through all these steps. So whatever we have discussed as part of this multiple linear regression in Python, we'll see, and we are going to find out the best model, and we'll use that for the prediction purpose. So these are the libraries that we need to load and load the cars dataset. So here we have total 5 variables, and so out of which the MPG, so miles per gallon, is a Y variable, and all other variables are independent variables, and some information related to cars. And do we have any missing values? Find out the correlation, right? So correlation between MPG versus HP, we can see negative, volume and SP weight, like that. You can find out the correlation. And so here we have the scatter plots. So on the diagonal, so boxes, you will find the histograms, and off diagonal, the uh, the boxes are the scatter plot. So this scatter plot is between MPG versus HP. You can see on that column HP and MPG. So this is scatter plot between MPG and HP. This is volume versus HP. Like that, you can find out all the scatter plots here. Right. Then build the build the regression equation. So SMF, so these are package, okay, and OLS, ordinary least squares. MPG, this is symbol is called as tilde, and these are the independent variables, all the independent variables, and then data set is a cars and fit the model. Okay, so parameters. So now we have got beta naught, beta 1, beta 2, so on and so forth. So our regression equation is like this, right? So y is equal to r. Let me write it with this. So MPG is equal to beta naught plus beta 1 and weight plus beta 2 volume. HP. Right. So these are the coefficients of these parameters. Now MPG equal to beta naught. Beta naught value is 30. Okay, 30 point something. Beta 1. Okay, beta 1 is 0.40. Weight. So likewise, so just take all these, the corresponding coefficients for these parameters, and plug into this. So then place beta 4 HP. So that is minus 0.205 into HP. Right. Now successfully we have estimated these betas. Now what you can do, so I have a new car. Okay. So for this car, I want to find out the MPG values. Simply take these cars, the weight and volume, SP and HP. So we can find out for this car, so all these variables, right? So once you find out those things, simply plug into this, then I'll get the MPG for this car. So that's how we can use this multiple linear regression equation for prediction purpose. All right. Now, so once we build the regression equation, is that end of the job? No, we have to validate. So we have to identify whether this regression equation is a good equation or bad equation, or any improvement is needed. All these things we have to evaluate as part of our flow, the workflow we have seen, right? Okay. So t values and p values to find out which variable is good, significant variable, and which variable is not significant variable. So as we discussed, if the p value is less than 0.05, then we can see there is a significant variable, and here these are the t values and these are the p values. So you don't have to consider this p-value whether it is less than 0.05 or more than 0.05 for intercept. Okay, so you can just ignore that. From weight, from the variables you check. So this is more than 0.05. So these are more than 0.05. These are less than and these less than. That means so these two only significant variable that we have seen in the presentation yesterday. So just keep that in mind, and we are going to do a series of exercise experiments, right? Then r square value 0.77 like that. Then we are building simple linear regression equation only on volume to check whether it is significant or not. Yes, it is significant. You can see this 3.8 into 10 power minus 7, and this is with weight. This is weight and volume. Right. So then we are computing the VAF. So this indicates, so when you combine weight and volume, we can see the p values become bigger, more than 0.05, right? So earlier, so when you have only the simple linear regression equation, the p value is less than 0.05, and that indicates there is a problem with these two variables that is called as multicollinearity. So to detect or to identify multicollinearity, we'll go for the VIF, so variance inflation factor, and yesterday we have seen this formula 1 by 1 minus r square of j. Okay, so let us compute the VIF values for each of this, and so 19 for HP, WT 639, 638 for volume, and 20 for SP. So this is what we have seen yesterday, and if the values are more than 20, we can say those variables are involved in the multicollinearity. Fine. Just we have to make a note of that, which are the variables are involved in multicollinearity, and then we can the remedy for this is just go for subset selection. That means so discard one variable and build the regression equation and find out the r square value and AAC values. And then like that, you remove one variable at a time and find out r square values and AAC values. The best subset should have the high r square value and the lowest AAC value. Then test for normality. So we are going to do the residual analysis or model validation techniques. So the first one is the test for normality, wherein you can see all the data points. If at all the data points are exactly on the solid red line, then we can say the residuals are following normal distribution. And this is one data point that is violating very far away, so from this, and this is also one more data point. So we can get the indexes of these data points. That means what is the row numbers of these data points. Okay, so these are the indexes of those data points, 0 and 76. Then standardize the data points. Then this is the plot that we have seen. Standardized fitted values, okay, versus residual values. The fitted values are nothing but y variable, y hat, predicted values from the model, and this one is the errors. And then a regressor versus the predictors. This is for this is for volume. Okay, so errors versus volume, and this we have seen. If you find so any patterns in this plot, then you can think of how to transform this variable, or your model is not a great model. Okay, and then like that you have to go for all the variables. So same regressors versus SP here, and regressor versus HP you have to examine. So here clear case of the pattern here you can see here. So how it is happening? So it is going down, okay, then it is going up. You see the HP is exhibiting a non-linear pattern with residuals. So this is what actually we were talking about. That means the HP is entering into the regression equation non-linearly. So this is a non-linear behavior. Okay, so this has to be straightened. So how we can straighten this relationship? So we have to go for transformations. So the transformation could be, you can think of x square is one transformation. That means instead of using uh, HP in the regression equation, y is equal to beta naught, okay, plus beta 1. Instead of using HP, what we can do is use HP square. That means square all the values in the HP column and use this. So this is called as transformation of the variable. Okay? And if at all, so in the residual plot, any variable exhibits this kind of a non-linear relationship, then the square transformation is the best transformation that you can apply. Okay? So did you find out the accuracy for this problem? The R square value was how much it is? 0.77, right? Okay. So like that, we have to find out for all the variables for weight also. Yes. Right. So once we identify so the problems so associated with the regression equation, then we'll go for the model deletion diagnostics, right? Right. So this is the Cook's distance. These are the values of the Cook's distance, right? So if you plot it, right, so this is a data point where you can see the maximum value that is more than 1. So this data point we are going to remove. So what is the data point? That is 76 observation. So this is 76 observation from the data, and the value of the Cook's distance is 1.08. And this is more than 1, and this data point has to be removed. As well as let us find out the influential data point, that is leverage. Okay, leverage. So let us find out the leverage, the cutoff for this. So in this case, for this data set, the leverage cutoff is 0.22. That means any data point that appears after this 0.22, then those data points are influential data points. Okay. Right. So since the 76th observation, so you can see 76th observation as well as 70th observation, they are outlets as well as influential data points. Remove those data points. So these are the two data points you can examine here: 70th and 76th data points, HP values, MPG. You can compare. So this highly influential outlier data points with the normal data set. So for HP, you can see 283, 22, and normal values of HP is 49, 50, 70, below 100. So that is where actually you can see, because of this high values in the HP, okay, as well as low values in MPG. So this data point, two data points, so term as the outliers. Then what we can do? Let us improve the model. So earlier we had seen the accuracy of the model is 77. Now after removing these two data points, outliers, let us see whether the accuracy would be improved or not. Okay, so we have removed the data points, those uh, two data points, 70th and 76th. Okay, and now here we have 79 rows only instead of 81. Build the model. So R square value. So how much is R square value? 0.816. That is 0.82. From 0.77, the R square value has been increased to 0.82, and AC value 446. Okay. Then let us remove. Okay. So let us remove volume. So as part of the exercise, we thought of remove one variable and keep track of R square value and AC values, right? So in that, so we identified volume, so has to be removed, and HP has to be included. Okay. Right. So here, if you see this, so here it is a 0.82, and without volume and with weight. So we have AC values 446.1, and here 446.11, and this 18. So that means when you include weight in the linear regression equation, AC value is more, a little bit more, R square value is a little bit less. So after comparing after the R square value and AC values, what we can conclude is volume, so we can retain, and weight has to be removed. So this is based on the subset selection in order to avoid the multi-collinearity problem. So that is what we can conclude from this. Okay. Now, the latest model again go for this Cook's distance, and this is 77th observation. Okay, 76th observation where we have again got the high AC the Cook's distance value. Remove that also and build the model again here. And these are the steps we are giving. We are repeating multiple times. So just to ensure that we don't have any influencers outliers in the data set. Okay. Yeah. So these repetitions might be confusing for you. So once you get this, the notebook, Python notebook that we are going to send you. So when you practice it, so that makes sense to you. But the flow is same. Whatever the diagram that I have given you, we are just going through that flow. Okay. So now till this point of time, we have removed all the outliers. We don't have any outliers and influential data points in the data set. Now with the cleaned data and with the shortlisted variables, we are going to build up model here. So that is, we have volume, SP and HP, and we have removed outliers from the data set. So with this, so if you see the R square value, so R square value is how much it is? 0.866, 0.87. That means, so when we build the regression equation initially, how much was the R square value? 0.77. So after doing series of steps, removing the outliers and removing the variable which is in multi-collinearity with the volume, okay, after doing these steps, the R square value has been increased to 0.87. This is the final model we would settle, right? So then using this model, we are going to predict for a new data. You can think of these are the new values for a car. So yesterday we have seen the car value, right? So we have given a few values to the website, and you can think of these are the values we are giving. 102 is top speed, volume is 95, and HP is 40. These are the values we are giving to the model. And let us see for this car, how much is MPG? Okay, MPG is 46. 46 is MPG, miles per gallon, for a car with these characteristics. Yeah. So like that, we can build a model and improve the accuracy over a period of time by evaluating the different aspects of the model and remove the outliers and influence observations. And once you build the final model with a good accuracy like this, then you can use that model for the prediction purpose. All right. So that's how we can follow the process of the model building. Right. Right. Few questions. Yes, we would be sharing this notebook and data files. Don't worry about that. These are outliers. That's right. If you have multiple columns, we cannot manually check like this, and how we will handle in real time. Yes. So if you have many columns, let's say you have 100 columns or 500 columns, yes. So we would encounter problems where we have to use many columns like that. So in that case, yes, this methodology is not going to be feasible for us. For this, we are going to discuss machine learning, the algorithms. That would be the next week. Yeah, but when you're learning the data science, yes, so this is the basics of the, you can think of the machine learning or linear regression. Yeah. So this model building are named as data cleaning and data mining. No, you cannot say this is a model. This is a model itself is a model, right? Twitter data is it possible to model? So that is based on the business scenario. So what we want to do with the Twitter data? Yeah, we have different use cases. For example, we want to find out the sentiment analysis. The Twitter. So the person has tweeted, right? That is a positive sentiment or negative sentiment. That means about a movie. Let's say, for example, so there is a tweet. We want to find out the tweet is positive about that movie or negative about the movie. Okay, so that we can find out. So you can say there is a classification problem. So flood prediction. Um, I'm not sure whether with this Twitter data we can predict the floods. See, that is a deterministic. If someone has tweeted about the floods, we can say yes, there are floods. So that is a simple the named entity recognition and another technique in the NLP that we can use it. So need not be a prediction model for this to identify the floods are there in an area or not. So can we reduce features using linear regression? You can, yes, you can do that. You can reduce the features using linear regression. So as we discussed, the hypothesis testing, right? T test. So you can find out which variables are significant, which variables are not significant. You can use that test to identify the best features out of the features that we have here. But we have more sophisticated feature engineering techniques we are going to discuss as part of our machine learning algorithms. All right. Okay, so let us take a break now, a 5 minutes break. So after that, we are going to discuss about logistic regression. Okay. Monday class is there. Yes, Monday a class is there. So tomorrow, Saturday, Sunday will not have any classes, but Monday, yes, we'll have class. Can we use lasso ridge here? Yes, we can use. We are going to discuss as part of our regularization methods, how to control the overfitting and all those things. We are going to discuss lasso ridge also. Yeah, I'll show you deployment. So of one algorithm, I'll show you that. All right. So 5:48. Let us take 5 minutes break. Then we'll continue our discussion after that on the logistic regression. Right. Yeah, hello everyone. Let us continue our discussion. Yeah, this is part of data mining. Okay. Yeah, now we are going to discuss about logistic regression. Right? Now let us understand. So what is the difference between this linear regression and logistic regression? So when do we use logistic regression? And first of all, why do we use this? So if you recall the two examples that we discussed as part of the linear regression, one is newspapers data, where we have the daily variable and Sunday variable, right? If you see the nature of these variables, both are continuous in nature or the numerical, you can say, especially the Y variable. Sunday is a circulation, right? So 5,000, let's say for example, 5,000 K or 2,000 K. These many circulations you can expect. These are the numerical values. And the other example that you discussed about that we discussed about the MPG, miles per gallon, the Y variable I was talking about. Y variable is miles per gallon. We have other X variables. So we are not interested in X variables, but only the Y variable. What is the nature of the Y variable? So this is a continuous variable like, okay, 40 or 20 or 15 or 8. So like that. So we have the different values and which is a continuous in nature. And if you see, these two are numerical Y variables. And the real life problems would come up so with only the variable in nature are the continuous the variables. If you see the real life problems, that may not be the variable Y variable is a numerical variable, so it could be different forms. I meant, so it also could be like yes or no kind of thing. The Y variable is yes or no. So, for example, if you want to find out a patient has a cancer, the Y variable is a patient has a cancer, that patient did not have the cancer. All right. And in the banking industry, so if you want to find out a person um, who has applied for a loan, that person is going to be defaulter, yes or no. So, this is another Y variable, a real life situation. The another example, a student so is going to be placed in the campus interview, yes or no. So this is also another example. That means, so the Y variable need not be the numerical variables like this. It could also be a categorical variables like this, yes or no kind of thing. So in this case, can we apply our normal linear regression equations, or do we have any specific kind of different kinds of the regression equation we have to apply? So in case of Y variable is a binary variable like this, yes or no, or the categorical variable like this, then we would apply logistic regression equation. So in this scenario, okay, so the logistic regression equation would apply when our Y variable is a binary variable, yes or no kind of a thing. There we'll apply the logistic regression. Okay, and why can't we apply? So why can't we apply the linear regression? Yes. So the simple linear or multiple linear regression equation. We will see what happens when you apply the multiple linear regression equation in a logistic regression. So this logistic regression also comes under the family of linear regression. This also comes under the linear regression, but so the way we use or the mathematical internal mechanism of how the math would work. So in this logistic regression, that's where actually the name the logistic regression, but this also comes under the family of the linear regression only. Right. So when we have a qualitative data in the Y variable, in the dependent variable, So where the y variable would be a binary response variable. So where we can say yes or no or 0 or 1. Okay. So in this case, we'll use logistic regression. So you can also say the logistic regression is a classification algorithm. So we'll discuss what do you mean by classification algorithm. And so when we have the categorical variable in the response variable, that means y variable or dependent variable, then we'll use logistic regression. In this case, logistic regression is to find relationship between the features and the probability of particular outcome. Let us say, for example, have a data set like this. The data set is uh, the bank in industry. These are the X variables, the applicant age, okay, so applicant salary, so who applied for a credit card, let's say, or who applied for a loan, salary and current EMIs, okay, and the number of dependents and all these things. So we'll have to fill in as part of the application, right? And then the Y variable, and here we have the different customers, customer 1, customer 2, customer 3, like this. And Y variable is, so with this customer, the characteristics, so this customer became defaulter and this customer did not become defaulter and defaulter. So like that we have the Y variables. Now using using this data set, we would build the regression equation. And once I build the regression equation, the logistic regression equation, then there is a new customer who applied for loan. And this new customer data I would input to the model. Then the model would throws out the probability of, okay, so y equal to defaulter or not a defaulter based on the code. Let us say what is the probability that this customer would not become defaulter given the customer characteristics. That means, so after giving the customer data to this model, what is the probability that this customer would not become a defaulter? Let's say this is 90%. That means there is a 90% probability that this customer would not become defaulter. Or so there is, let's say, 50% chance that this customer would become defaulter. That means as part of this logistic regression, we are going to find out the probability of whether the customer is going to be defaulter or not. So this is what we are going to find out. Yeah. So what are the examples? The examples, as we discussed, uh, based on the different the parameters of health, okay, like age, so age, sex, smoking, okay, diet, and family medical history. Based on these characteristics, whether a particular patient so had a cancer or did not have a cancer. So y equal to 1 or 0. That means how the data set would look like. The data set is like this. So I can have here, so age, okay. So here we have sex, and here we have smoking habit, okay, yes or no, and all these things, then Y variable. So first patient, so age 35, here male, so smoking yes, cancer yes. So second patient, so like that, this is my data set. And when you say y equal to 1 or 0, so I can replace this y with 1 and 0, 1 0. This also another representation of the y variable, so for this binary response variable, right? So this data set we are going to use for building of the model. Right. So here we have a two critical questions. So on this data set, whatever the data set that we're talking about, the y variable is a binary response variable. For this kind of data, can we run a usual linear regression and interpret the outcome? Okay. So let us run that. What happens if if I apply normal linear regression equation on this the binary response y variable data? And then such response variable is a qualitative in nature. We are talking about y value 1 or 0, 1 or 0, right? That means yes or no, yes or no. So in this case, what do you predict in this case? What do you predict? So as we discussed, we are going to predict what is the probability that y is equal to 1 given, so that customer records, that customer characteristics are, so that example, that observation, what is the probability of that? So this is what actually we're going to predict as part of this logistic regression. Now, so these questions we are going to answer so with example, a business problem. So just take a few seconds, read this. We are going to discuss this problem statement. So please read this. So if you understand this, then it would be much easier for you to understand whatever the things we are going to discuss. Please read this and we are going to discuss. So this is a business problem. All right. So let's have a discussion on this now. So this is related to insurance domain. The data set, so data set has 1340 bodily injured liability claims from a single state in USA during 2002. The data has been collected using a survey conducted by a research organization, that is Insurance Research Council. And what is the objective of this? The objective of this is, let's say for example, in US, what happens when someone want to settle a claim, when someone want to file the claim settlement documents. So what they do is, so they have two options. So there is a person here. So this is a customer, a claimant who has insurance and who has met with an accident to claim that insurance money related to that accident. So this person has two paths to submit the documents. One is, so this person can go through attorney, a lawyer. Attorney is nothing but a lawyer. So this lawyer, on behalf of his customer, her customer, would file this the claim settlement form with the insurance company. This is insurance company. So this is one path. The other path is, so this customer, so herself or himself would file the claim settlement process, or would file all the documents with this company. Now, what happens? This insurance company wanted to understand, before giving the insurance policy to any customer. So this customer wanted to buy insurance policy. So this customer would approach insurance company. Before buying or before selling that insurance policy to this customer, insurance company wanted to understand why the settling the claims, this customer would follow the process one or process two. The approach one through attorney, or so they themselves would file the claim settlement, everything. So why this insurance company wanted to understand whether this customer would go through attorney or this customer would file all the documentation by themselves. What is the interest for the insurance company? Because if a customer goes through an attorney, so like this, okay, so this attorney knows so all the loopholes, okay, and all the queries generally raised by this insurance company, so that this attorney can effectively answer those queries, so that the amount can be maximized for his or her customer. So in this second, let's say this is the first way, this is the second way. So when the customer files the settlement claim by themselves, in this way, the insurance company can raise a lot of queries, and so definitely they can deny some of the components in the insurance amount. That means they can reduce the money that goes to the customer. In the first instance, so the company has to shell out more money. The second instance, they don't have to shell out more money because the customer, they cannot answer all the queries raised by this insurance company. That means the insurance company wanted to understand if a customer is going to approach the attorney in future, or the customer is going to file the all this the claim settlement process by themselves. So if it is first path, then the company has to lose more money. If it is second path, the company need not to pay more money because they can decline some of the components in the insurance claim. Now, the situation here is the IRC, Insurance Research Council, so is founded by various insurance companies. So these guys wanted to understand what are the customer characteristics that would approach the attorneys, and what kind of customers would go through the second path. If I know upfront before selling any insurance policy to this customer, if at all that customer is going to be followed by first path, then I have a different plans altogether. So I'll increase my premium amount, so that even this customer goes through the first path, then the balance that transactions would be balanced out, because I'm going to charge them very high premium amount, and that guy definitely would go through the attorney, then this whole transactions would be balanced out. If a customer is going to be followed this second part, then I'll sell different plans altogether, different policies altogether. The premium rate would be low. Then definitely this guy is not going to be represented by an attorney. Then I don't have to pay more money. So this is a whole logic why we are doing this exercise. Let me repeat quickly. Okay, so then I'll take the questions if you have any. So the whole exercise here is, so this Insurance Research Council, they wanted to understand what kind of customers so are going to be represented by an attorney when settling the claim. Okay, so that means, so the gender wise, okay, age wise, the marital status, what kind of customers. So they are going to approach the attorney in future while settling the claim. So when they met the accident, so they'll have to file the insurance documents, right? So during that period, are they going to approach the attorney for that process, or are they going to represent themselves without contacting the attorney? So why these insurance companies are interested to understand, so whether they are going to approach attorney or not. If the attorney is represented, so in that case, then the company has to shell out more money. Otherwise, they don't have to shell out more money. Okay, so this is the scenario actually. Now, so upfront, the insurance companies wanted to understand before selling any insurance policy to a customer, whether this customer is going through this first path or second path. If at all the customer is going through the first path, then they'll have a different policies altogether. Then they'll have a higher premium rates for this kind of customers. So otherwise, so they'll have a different plans or policies altogether for this second category customers, and the premium rates also low. So this is the whole objective of this business problem. Yeah, let me know if you have understood this clearly or any questions on this. So you can say yes or no. Yeah, anything is fine for me. So if you say no, then we'll have a discussion one more time. Okay, great. Right. The data set here is, excuse me, the data set that here is the climate data set we are going to consider. I'll show you the data set in a moment. And the variables that we have here is attorney is one variable. This is the Y variable. Attorney is a Y variable. And these are all other variables that we have. So climate, age, so climate, sex, whether the claimant was wearing seat belt. Okay. And so that guy is okay, insurance, uninsured, okay, and economic loss. What is the total economic loss in that accident, right? So these are the different the variables that we have in the data set. Let me show you the data set just to see the how the data set looks like. Just give me a minute. This content. Right. So this is the data set here. A case number, you can think of a record, unique identification number, just like your the student ID. Okay. And attorney. This is my Y variable. So if attorney equal to 0 means, so this customer, first customer, has appointed an attorney to represent himself or herself. So with this insurance company, that means just he has hired an attorney. So claimant 6, 0 or 1, insurance, seatbelt, claimant age, and total economic loss in that accident. Now, so the regression equation that we are expecting here is attorney. Okay, so the lawyer, so y is equal to beta naught, okay, plus beta 1, claimant 6, plus beta 2, we have insurance, plus beta 3, like that. So we have all the variables. Now using this data set, we are going to estimate these betas, okay, these betas. And once we have got these values, then we plug into this, then we'll use this regression equation for the prediction purpose. Once you build this regression equation, so how are we expecting to use this regression equation? Imagine there is a new customer. So this customer has approached the insurance company. This insurance company, just think from the insurance company perspective. Just imagine that you are working for insurance company. Now you will collect this the customer data as part of the application, right? Now this data you would feed to the algorithm. Then algorithm would give you the details. So the probability of this customer, okay, is not going to represent by an attorney given the customer application details, customer characteristics based on the age and gender and insurance and all those things. Okay, then my algorithm would throw out the probability value. The probability value, let's say for example 0.9. Okay, 0.9. That means 90% probability that so this customer is not going to be represented by an attorney. That means so this guy would not hire an attorney with a 90% probability. So in this case, what I would do, so as an insurance company, so I would sell a low premium, a low premium. That means the customer has need not pay the high amount for the insurance, right? So this guy can get within the low premium rates. That is good for the customer. If a customer, let's say for example another customer is there, so this customer, when I details, when I feed it to the algorithm gave me the probability of y equal to 1 given the customer details is 0.1. That means there is 10% probability that this customer is not going to be represented by an attorney. That means so there is only 10% probability that this customer is not going to hire the attorney. That means there is a good chance that this customer is going to hire the attorney. So if that is the case, I would sell him a high premium rate, because anyway this guy is going to represent by an attorney when settling the claim. That means so this guy is going to get more money. So I'll have high premium rate. That means yeah, so I'll sell the insurance policies for high rate. This guy has to pay more money to buy that insurance. So that's how we are going to use this logistic regression. So this is a whole entire business scenario. Loss is a continuous variable. No, that is not a categorical. It's a continuous variable. Right. So regression equation is like this. So y is equal to beta naught plus beta 1 d1. D1 is nothing but these variables. In place of x1, just we change the notation d1, d2, so on and so forth. Right. Now, when I apply this linear regression on this data set, Okay. Linear regression on this data set, I have got the output. You can see here the output of the linear regression and intercept and insurance and seed wealth loss and all those things. You can also see the p values for each of these variables, and wherever you see less than 0.05, you can say those are the significant, right? Otherwise those are not significant. Okay, so let us put that aside. Let us not get into the details of whether they are significant or not. And the R-square values, how much it is, multiple R-square values pretty bad. 0.06 is very, very low. That's okay. Okay, but the major problem that we have here is when you apply the linear regression for the data where the y variable is dichotomous variable, that is the binary variable, binary response variable, what happens? The predicted value. So what we thought, the predicted value or the output of the regression equation should be a probability value. Okay, y equal to 1, given the customer details, then I'll get the probability value. So probability value should be between 0 to 1. Okay, but so when I apply this linear regression equation on this data set, okay, and when I predict, I have got these values. So 0.48, that means there is a 48% probability that so this customer is not going to be represented, and is 45%. What about this negative 0.15? Is this a probability? No, right? This is not a probability. We thought of using output as a probability, but so here we have got the values as negative values. Okay? And there is also chance we might get the values more than 1, because we are using a linear regression equation. What does it mean? So here we have a line, right? There is a line. So in this case, when you have multiple variables, it would be a plane. But so if you say the line, we do not have any bound for this line. As long as the x increases, the y also increases. Y also increases. Right? And that is what happening actually with the linear regression. There is no bound for this, but we are talking about it should be between 0 to 1, but there is no bound for this linear regression equation. It can go, so as long as the x increases, y also increases. It goes beyond 1 or it goes below 0. And in this case, we cannot interpret the values. Okay. Now, so the problem here is with this linear regression equation, we thought of using these values as a probability values, but here there is a chance of getting the values less than 0 and more than 1. That is a problem. Okay. So not all predicted values lie between 0 and 1. If at all, so if you have the values have between 0 and 1, then I would have used this as the probability values. So in this case now I cannot use so as it is, right? Now so since we discussed the output of linear regression equation, the linear regression equation so are negative values as well as which are more than 1 also. Now what I'm thinking is, so if you have a mathematical function, okay, a mathematical function which can transform these values which are any value, so it could be negative 0.5 or more than 1, let's say 10 or like this, so any value. So if any mathematical function can transform these values into a domain of 0 to 1, that means the probability 0 to 1, then I can use so these values as a probability values and I can interpret, and then so I can use these as predicted values. So now whatever the values that I get from the linear regression equation, so I'll just pass it through a mathematical function, and this function should transform the values. So whatever the domain that might be, so it should it should transform those values to 0 to 1. So it does not matter how low that value is or how big is that value is. Always I should get the values output of this mathematical function should be 0 to 1 only. And this mathematical function is a logistic function. And what we are going to do is, I'll take the output of linear regression, then I'll pass it through this mathematical function, then I'll get the output, and these values would be always between 0 to 1, and I can use these values as the probabilities. And that is what we are expecting. And that mathematical function is logistic function, and this is what the logistic function is. And the behavior of this, the property of this logistic function is, no matter what, how big or how small the value that you pass to the function, always I'll get the values between 0 to 1. always I'll get this between 0 to 1. Does not matter how big or how small the values are, right? And if you see the comparison between these logistic function R, this also called as sigmoid function. This is my linear. A straight line is a linear line, and this one is a logistic or sigmoid function. If you see the behavior of this one, let us compare these two. On x-axis, I have the x values. Let us say my x is here. X values here. You can think of simple. So x is experience. Y is salary. Okay. So this experience is 1 year. So I can say this 1 year. And what is this salary? So if you use this, for example, so since this is a negative, okay, so this doesn't make much sense, but let me give you. The values are negative here. The values are negative, right? So if my x is here, so the value is here, a positive. X is here, the values are here, y values. This is y. And x is here, the values are beyond 1. So that means, so you cannot interpret this by, okay, so in this case as a probability when you use linear regression equation. On other hand, if you use this logistic curve, if my x value is here, the y values between 0 to 1, x is here, again between 0 to 1, so x is here, 0 to 1, it doesn't go beyond value of more than 1. Always it resides, it will be between 0 to 1. So that's how we can use the y values from this, the output values from this logistic regression logistic function as the probability values. All right. Right. Now let me show you how do we get this curve actually. So this is a curve, logistic curve. How do we get this curve? So let us take a simple example and let us see. So I've taken the input values as like this, -5 to +5. And what I would do is I'll give this -5 to my logistic function. That is 1 by 1 plus e power minus x. Okay. And so in place of x, I'll replace this x with -5. That is 1 by 1 plus e power minus of -5. So this value is this. So like that, input just replace x with -4, -3 like that. So I've got these values. These are the outputs of the logistic function. And you see the values are between 0 to 1. Okay. Now take these values and plot it. So I'll take these two values. So this is input is nothing but x and this is y. Okay. So this is a plot. So the plot is the shape of S-shaped curve. So when you have value of -5, what is the value of logistic function? Y 0.006. So this is where actually you can see -5 0.006. For -4, you have the values of 0.01. At 0, exactly that gives you 0.5. X is 0, the input is 0, the y is 0.5. And as you increase the x value, the max it can reach is 0.99999. Okay, so it doesn't go beyond 1. Beyond 1, how big your x value is or how low your x value is. So this is a property of logistic function, right? And this is what we need. What we do is, so as part of, so we have a logistic function, right? So this 1 by 1 plus e power minus x. What I do is, whatever my regression equation y, right? Beta naught plus beta 1 so and so, beta 1 x1, whatever the output that I get here, so that output I'll send it to this my logistic regression equation. So since we would get the values which are below 0 and above 1 also, right? So these values, when I use this logistic function, that would get transformed to this domain 0 to 1. Then these values I can use as probabilities. So that's the idea now we are going to discuss. Right. So our equation is this: the y probability of the y equal to 1 given the x, given the details of the input, the customer details. So that is beta naught plus beta 1 so and so. So these are uh, right. So linear probabilistic model. So this one, and then so as we discussed 1 by 1 plus e power minus x simply, so I'll take these values, this equation I'll represent here, I'll place here. Okay. Then that is 1 by 1 plus e power, so minus beta naught beta 1 and all those things. So let us assume that this is equal to z. So for a simplicity, then that would become, so 1 by 1 plus e power minus z, then this would become this. So just I can take out this minus z, 1 by e power z. So I can take the LCM and I can get this value, this equation, e power z by 1 plus e power z, where z equal to this equation. Okay. So since this is in non-linear terms to the right side, so now our equation is expected value of, so y is equal to 1 given the customer characteristics is equal to, so e power z by 1 plus e power z. This is my equation. So since this equation is in non-linear terms, right? So e powers and the ratios and all these things, right? So I want to convert this into linear terms. So for that I'll apply some mathematical procedure, like, so what I would do is I'll take the ratio. So pi, this is nothing but I can also say pi, this equal to probability pi. So I would apply pi by 1 minus pi, that is equal to e power zi. Then after again applying some mathematical procedure, I'll get this final equation, this one. So this equation is called as logistic regression or logit model. So logit model is log of, okay, pi by 1 minus pi is equal to beta naught plus beta 1, okay, d1 plus so and so. So this equation is called as logistic regression equation or logistic model, right? Now, so yeah, this equation is called as logit model. Now let us say, for example, I have a new customer. Okay, so this customer, so this customer has applied for a policy, for example. Now I'll take this customer the characteristics. Okay, this customer characteristics I'll take and I'll input to this model. So beta naught, beta 1, d1. D1 is a customer age, let's say. So customer gender and all those things, right? So I'll input to this. And let us say this value is 2. Okay, so this value is 2. Now, log of pi by 1 minus pi is equal to 2. How did we get this 2? So just input the characteristics of this customer into this equation, and we have already estimated beta 1 beta 2 from the data, and assume that we have got 2 as part of this equation. Now the log of pi by 1 minus pi is equal to 2. Now let us solve this to find out the probability. Okay, so pi by 1 minus pi is equal to, so this log, right? So we can take the e, so exponential e square. So approximately let us say e value or e square value here is 8. So e value is 2.71, right? So approximately 3 less than 1, we can say e square is 8. And then so pi is equal to 8 minus 8 pi. Okay, so just bring this 8 pi to this side, so that would be 9 pi is equal to 8, and p, so 8 by 9, and which is so approximately 90% or 0.99 0.9. So the probability is 0.9. What is this probability? So this probability is uh, probability of y is equal to 1 given this customer characteristics is equal to 0.9. Then how do we interpret this? The probability of the customer is not going to represent by an attorney. That means, so this customer is not going to approach the attorney while settling the claim is 90% probability. That means, so this guy is directly approaches the insurance company for claim settlement process. He doesn't go to attorney for that purpose. So in that case, then we can sell a low premium rate insurance policies, so that we can go ahead with that. Okay, and if at all, so this p value is, let's say, is so 0.2. That means there is a 20% probability that this customer is not going to represent by an attorney. That means there is a good chance, 80% chance, so this customer would definitely visit the attorney when settling the claim. So in that case, what we do, sell high premium the insurance policies to this guy, so that anyway this guy is going to represented by an attorney. Right? So in those process, it would be balanced out. So that is how for a given customer, I can use my elastic regression to find out whether that guy is going to be represented by an attorney or not. Again, if you see, that is yes or no kind of a question only, right? Yes or no, going to be represented by an attorney or not going to be represented by an attorney, yes or no. So like this, we will find out the probabilities. Now there is a few more things to understand here. What is this pi by 1 minus pi? Pi by 1 minus pi is called as odds ratio. And remember, in the logistic regression, every time, so the probability, whatever the probability that you get, so would be associated with y equal to 1, y equal to 1, given the x variable values. Okay. Now, so pi by 1 minus pi is odds ratio, and this odds ratio is the probability of success to the probability of failure. So this is a probability of success. So in this insurance case, okay, so just think from the insurance company point of view, when do you say you have got the success? If the customer is not going to hire the attorney, not hiring attorney, this is my success as an insurance company. Because so in this case, I don't have to lose much money, right? And 1 minus pi is failure probability, so hiring an attorney. Just think not from the customer point of view, think from the company point of view, because you are working as a data scientist with this company, so hiring an attorney. Okay, so 1 minus pi, hiring an attorney. So this is the probability of failure and this is a probability of success, because if a customer is not going to hire the attorney, that is my success. Okay, and if the customer is going to hire the attorney, that is a probability of failure. The ratio of these two is called as odds ratio. Okay. In the earlier case, if you see, 1 minus pi is equal to 2 in earlier case, right? So now I can say 2 by 1. That means the probability of success is more and probability of failure is low. And that is where we have got pi is equal to 80%. That means, yes, there are the odds, you can interpret like this. The odds are in our favor with the company that the customer is not going to hide the attorney. So if you get this value, so pi by 1 minus pi 2 means you can say the odds are in our favor from the company perspective. The customer is not going to hire the attorney. So that's how we can interpret the output of the logistic regression. Okay, there are a few questions. The range is between 0 to 1, but we are also getting the values less than 0. If you use this logistic function, we will not get the values below 0. Yeah. Right. No, yeah, these are the things that we discussed. Yes. Then how do we measure the accuracy of the classification? So in case of normal simple linear multiple linear regression equation, we measured using the R square value, right? So in this case, how do we measure the accuracy for the logistic regression? We would measure the accuracy for the logistic regression using confusion matrix. So this is a method we'll use to find out the accuracy of the logistic regression. And we have another terminology called sensitivity, specificity, and ROC curves. So let me quickly give you the idea of how we are going to construct this confusion matrix. Let us say I have the data points x1 and x2, x3 like this. And this is my y. And here we have y hat. Y hat is the predicted value using the logistic regression for given data. Let me write down here 0, 1, 0, 1. Okay, 1. We have 5. Okay, so 1, 0, 0, 0. Okay, 3. Okay, yeah, these are the 10 data points that we have in the data set. So this first data point, second, third, like this. The predicted value, like let's say for example this 0, 0, this 1, 0, 0, 1, 1, 1, and 1, 0, 0, 1, 0, 0, 1, and 0. Right. So then I'll build a matrix, a 2 by 2 matrix. So in this, so here we have actual data. This is the predicted data. Okay. This is 0, 1, 0, 1. Now, actual data means from the data set. This is my actual and this is my predicted data. Let us count how many numbers that are matching with 0, 0. That means actual data is 0 and predicted also 0. Okay. So just look for 0 here and 0 here. This one case, 2. So this is 2. Then this one, 1, 1. So this 1, 2. Okay, only 2. Then predicted 0, actual 1. So predicted 0 and actual 1. So that means, so 1, 0, we have to check. 1, 0. This is one case, this second case, and third case. So that is 3. And total we have 10 data points. This must be 3. Then the accuracy of this algorithm, we can find out by adding these diagonal elements. That is 2 plus 2. 2 plus 2 by 10. So that is 40% is the accuracy of this model, 0.4. So why we have added this only? Because my model correctly predicted. So if that is 0 means my model also correctly predicted 0. If the actual data is 1, my model also predicted correctly 1. So these two elements are the right predictions. Right. So these two elements are correct predictions. These two boxes. So these are wrong predictions. And that is where the right predictions you sum it up, how many number of cases the model has predicted rightly. So these two cases, so 4 by total overall, how many data points are there? 10 data points. Then that is 40%. So like this, predicted ones and predicted zeros, observed, these are actual ones and actual zeros. Actual ones and zeros. And based on this, so A plus D by total, A plus B plus C plus D. This is the accuracy of an algorithm, a classification algorithm using this confusion matrix. So this matrix is called as confusion matrix. And also we would find out sensitivity and specificity. The sensitivity is again A by A plus C and D by B plus D. So for a good model, the accuracy as well as sensitivity and specificity should be high. Okay, so that's how we'll find out the model accuracy, and so that's how we can build the concept of the logistic regression and the accuracy for this logistic regression. Right? All right. Okay, so that's all for today. Monday we will see how do we implement this in Python. Yeah. Right. So the precision and accuracy, yes. So there is a difference. The precision is similar to specificity, if I'm not wrong. Yeah. So accuracy is overall accuracy that you see. When do we use AUC and ROC? Yeah, ROC is a receiver operand characteristics. So that also will use to find out the accuracy of the model and based on the area under the car. Yeah, that also we can use to find out the accuracy, but confusion matrix is more common to find out the accuracy for the classification problems. So accuracy reflects how close measurement. Yeah. For imbalanced data, yes. So we would use sensitivity and specificity. Okay. More often we'll use F1 score that we'll discuss. F1 score would give us the right picture about the accuracy of the classification method when you have the imbalanced data. So rather than only measuring the accuracy or recall or precision, we are going to use both recall as well as the precision in the F1 score. Yeah, so that we'll discuss in the next class, true positives and true negatives. So when we build the algorithm, we are going to generate them. Yes. There is a question, your input on Tableau software for data analytics, is it used in industry? I did not get your question. If your question is Tableau software is widely used in the industry? Yes, Tableau is a leading visualization techniques in data analytics department. Yeah. So all right, so we will wind up the session for today. Yeah, so everyone, happy Deepavali. So thank you, and we'll meet on Monday.